All right, guys. Um, we are going to be continuing on with our ladder diagrams and our relay conversation that we were talking about. So up to this point, I haven't expressly explained the two sides, but we have two-wire control, okay? And two-wire control is when we have a switch and a load, okay? And the reason why it's called two-wire control is that if I had a junction box, and let's say I had a little pilot light coming off the side, and so that's my little pilot light, and I had brought power into the box, so let's say this was line 1 and a neutral, and I had another box over here that had a toggle switch in it, I would only need to run two wires, 1, 2, and put them on a little, so that's a little toggle switch with 2 screws on it. I would need to put one on one side, one on the other, and let's say this is my light. I would have my neutral goes to my little pilot light, and then the hot goes to one side over to the switch. I turn the switch on, sends power back to turn the light on. So two-wire control means I solely need 2 wires in order to activate that switch. The next thing that we've slowly started to build on is the thought of 3-wire control. So 3-wire control. And with 3-wire control, it's the circuit where I talked about we had our normally open switch. Then we have our holding contact around it, which everyone's done. And then we went to our light. And the reason why this is 3-wire control, and we'll put our little stop button in, and for some of the groups, 2 of the groups, I didn't get to adding that guy in. But this is our example of 3-wire control. So we have our stop button, we have the stop, and we have our holding contact that goes around that start button. So that would be PB1, PB2, and actually, sorry, that would be our light. That would be a coil. And we have our holding contact, and I'm going to call this CR1, which we haven't quite gone into. I'll explain the rest of it. But with 3-wire control, if I wanted to make this work, I would only need to run 3 wires in order to get that actually activate. So if I had a junction box, and my junction box has our little coil, and I had power coming into the box at line 1, and I have a neutral, and then I have another box over here. This box would have my normally open push button and would have my normally closed push button in it. In order to activate this, I'm only actually going to need 3 wires to make all this happen. So I'm going to have my neutral, or it could be my negative 24 volts, go to one side of the coil, and I'm just going to draw, I've got 1 wire, 2 wire, and I've got my 3rd wire. So I want to end up, and I'm going to have my I need to put in my little holding contact. So this is my holding contact. My holding contact's on the coil, so that when it energizes, it goes down. So I'm gonna have my first wire. So my first wire comes around and goes all the way over to this switch here, normally open switch. And as you can see here, I need to connect onto it. I connect onto that switch. The other side comes over to my PB2, so my normally closed push button. So I'm gonna just bring it down here, connect it on. The other side ends up going to my coil, so it needs to come back through to my coil, but then I have only one extra wire and nothing connected to my normally open contact. Well, if you look here, I can either bring one side off the coil from PB2 or from my coil. My coil is over here, so I can bring this over to my coil. And then the last part is this one here. So between my push button 1 and my stop button, I need to bring another wire around on, and it comes back. I'm just going to jump over the wire and comes back to my coil. And that's my 3-wire control circuit. I hope that makes sense and was fairly clear to you. So it doesn't matter where I'm controlling stuff, I only need to send a 3-wire over to my my start-stop station, which this would be where I have a stop or a start, the normally open push button, and I have a stop, my normally closed push button. I'm not going to ask you about this, I'm just showing you that you only need 3 wires for that to work. So that's only the difference. So if I ever ask you to wire a 2-wire control circuit, all you're going to be doing is doing the first one where you have a toggle switch or a normally open button just to turn the light on and off. But if I ever ask you to do a 3-wire control circuit, or I ask you about 3-wire control circuits, I'm going to be asking you about this where I have a coil and I have a holding contact. Okay, so let me just redo this. So we had, starting out, we had our normally closed push button. So this is my PB1, and that's a normally closed push button. It comes out to PB2, and that is a normally open push button. Now I have a set of normally open contacts, and these normally open contacts, these are my holding contacts. And a couple of the groups, when they went to go through, we had just got this part done with our coil. And this is my 24 volts positive, 24 volts negative. We just got that far, and we didn't actually put that stop button in, but that was the next step. So where we had left it before is once that push button's pressed, it energizes that coil, which closes this normally open set of contacts. The problem from this point is that you couldn't turn it off, and here was that last step where you put in that stop button. What's really important too is when you have coils like this, it's important to make sure you address everything. So and label everything the way it's supposed to. So here I have, it's rung 001, and this is rung 002, which falls along this side. I need to tell whoever's looking at this drawing what normally open contacts are connected to that coil, because if I have a ladder diagram, I could have multiple coils in it, I could have multiple normally open contacts for every coil, or normally closed contacts. So in this case, my coil should tell me that on rung 002, and I made that a little close, that side. I need to write, and you can do it as a dash line or solid line, but I like to write it as just normally open, okay, and 002. So now if someone goes to look at this ladder diagram, they can see that that coil has a normally open contact on 002, which is right here, and this coil here is CR1, and this is the associated normally open contact to that one. So I write CR1 here, just so that when you look at the coil and you look at the normally open contacts, you know that they are connected with each other. Because I can also have multiple normally open or normally closed contacts on the exact same rung. So you need to make sure that you identify all those. Okay, so that was our holding contact. And what we talked about in class example was 9 and 5 on the little ice cube relays that we were using. And this was A1 and A2. And then we had our normally closed push button. You would have labeled it 119, 120. This one, the normally open, would be 113 and 114. So that's very important to remember, that when I say 3-wire control, that is exactly what I'm going to be talking about. And then from here, and I'm going to get everyone to wire a little bit more in the next class. But we also have an extra rung, or more rungs we can put in. I'm going to have another normally open contact, and this is going to be a green pilot light. So this is PL1, right? And so this is also connected to CR1, so I need to label that CR1, and I also need to label up here that on rung 003 I have another normally open contact. I can then add on top of that, so we had talked already that this is the symbol, right, for a normally open contact, and we also have normally closed contacts. And a normally closed contact, when the relay is not energized, it's in the closed state. Normally open contacts are in the open position when the relay is not energized. But if I do the next rung down, and I do a normally closed contact, and make this a red pilot light, I end up seeing that this is also from CR1, but it is a normally closed contact, and it's on rung 004. So the addressing is extremely important. This very likely could be 10 and 6, and I believe this would be 11 and 3 if I remember correctly from the relay. So hopefully you can see everything that's on here, and then that would be a typical ladder diagram circuit. One thing I want to show you is that there are also other ways where you can simplify this. So if I was going to look at this circuit, when I press down my normally open push button, or my start, and this would be a start stop circuit, if I press down that start, it energizes that coil, which closes that set of contacts. So as soon as it's energized, that closes. Something you can add on to this, rather than adding an additional rung, is I actually could come off here and add another one here. So if I added that one there, I really could completely lose this rung. And if you analyze this circuit, you're going to see that there's no power coming through this start button, no power coming through that normally open contact, in order to energize G. If I go to press down PB2, it energizes the coil and sends power to the green light at the same time, but that's the exact same thing that would have happened if I push that down. It would have energizes the coil, which would have closed the normally open contact that was here and turned the light on at the same time. So in that, I push it down, coil energizes and closes that normally open set of contacts. It illuminates the green pilot light, and when I take my finger off, everything remains energized because of that holding contact. And just like if I still had that rung there, none of this would turn off until I hit stop, then everything would then de-energize. A very important thing I haven't brought up yet, but is something to very much keep in mind. And obviously I changed the labeling there. I would take that off there because I wouldn't have that rung, and change that to 003. But a very important thing with ladder diagrams, and not just ladder diagrams, but when you're wiring things up. If I have a toggle switch here, and then I come out and I do a green light, is there a problem if I add in an additional light on the same rung? And this is something you also get into in electronics, and you'll get into it in theory class, is that in all the other examples that we did, and when we had multiple loads, they were all in parallel. I would only have one load per rung. So my green light would be on this rung, another rung would be on that rung. But in this case, I have two lights on the exact same rung. And initially, if you look at this, you may not think that there's much of an issue. I've got power coming in, power going out. But where the problem arises is that I now have both of these lights in series with each other. You typically would have seen that when you have Christmas tree lights, and if one of the lights burns out, all the rest of them burn out. But if I go to close this switch, let's say this was 120 volts, and this was my neutral. So I've got 0 volts here. So 120 volts, 0 volts here. And let's say that both of these had the same drew the same current. Let's say at 120 volts. So at 120 volts, let's say they drew 1 amp. So at 120 volts, that one draws 1 amp. At 120 volts, that one draws 1 amp. And when you look at a circuit like this, what you really have to break it down to is what is the resistance of each of those pilot lights. And it doesn't necessarily just have to be with pilot lights. It can also be with an incandescent bulb, halogen bulb. But if I take 120 volts divided by 1, and if I'm looking at Ohm's law, right? So break it way down is E is equal to I times R. And if I want to get I by itself, I need to divide resistance out. I don't want to get I by itself. I want to get R by itself. If I want to get R by itself, I need to divide I out on both sides, like that. So my formula now becomes R is equal to E divided by I, which is 120 volts divided by 1 amp. And if I do 120 volts divided by 1 amp, I get a resistance of 120 ohms. And if you check on the calculator, you'll see that that's the same. So that's 120 ohms, and this one's 120 ohms. So I have a total voltage of 120 volts. That's supposed to be dropped across the entire thing. But I now have 120 volts on the same rung rather than, or 120 ohms times 2 on the same rung. And if I go to recalculate this formula, if we look at a series circuit, in series circuits, I add up my total resistance. So my total resistance now between the two of these is 240 volts, or ohms. I don't know why I keep saying volts. So 240 ohms. If I go to calculate the current that now is traveling through that, 120 volts divided by 240 ohms, because I want to calculate current, and we did that. We can do that by E is equal to I times R, and then dividing resistance out on both sides, right? We get a formula is I is equal to E divided by R, so 120 divided by 240 ohms, and we get an answer of either 0.5 amps or 500 milliamps, but let's just say it's 0.5 amps. So 0.5 amps, and that 0.5 amps is going to see, if we put an amp clamp on there and test that, we see 0.5 amps through the entire thing. So my green light's going to see 0.5 amps, my red light's going to see 0.5 amps, and if I now take my resistive value and my ampacity and figure out what voltage is, which is I times R, and I do E is equal to 120 times 0.5 ohms, or 500 milliamp. I want to do, yeah. I did that backwards, so. Sorry. 0.5 amps times 120 ohms. If I take both those values and multiply them together now, I see or find that now I only have 60 volts dropped across that light and 60 volts dropped across that light. So typically, in a situation like this, I would get 120 volts dropped across one light. Now I've only got 60 volts dropped across that light. So not only did I drop my voltage by half, my ampacity, which is supposed to be 1 amp, is now only half an amp. So what you find from this is that these lights are now going to be dim compared to what they normally would. If you put loads in series, they end up splitting the voltage between them based on how large the resistance is. So you always have to remember, don't put more than one load on a rung. So you only put one. So that red one that's in there would have to go on a different rung. So always remember that. Okay, so we're going to finish up with a little bit on the ladder diagram stuff. I'm going to have you do one more little circuit in class, in your next lab class. But what I want to get onto now is pressure. Pressure. So we have pressure is equal to force divided by area, or P is equal to F over A. And let's break that down a little bit. So pressure, what would you typically see as a pressure? What's the most common type of pressure? Well, if you look on a tire gauge, typically what you're going to see is a number that's in PSI, right? So if you go fill your tire up, you're typically going to fill it up to around 30 to 38 PSI, depending on the size of the vehicle. Force is a value that you would typically see as a weight in example is pounds or kilograms, and whatever you decide on for your measurement of weight, you'd have to keep your, if you're doing pounds and then inches, keep them together, or kilograms and millimeters or meters together. I'm going to just use pounds right now, divided by our area, and an example of an area is inches squared or squared inches. So if you look at this here, and the fact that we are measuring in PSI, PSI is pounds per square inch, okay, which is exactly what this formula ends up indicating. So where I want to go with this is, let's say I have a tower. So that's my tower, and the bottom of my tower is 2 inches by, let's say, 3 inches, and it weighs, let's say, 60 pounds. And I want you to find out what the force is that's on the bottom. And I'll just say that this tower is, let's say it's 15 inches high. And I want to take out from this question what the most important information is. Well, what is that most important information? Most important information is we need to figure out the area of the bottom, right? We need to figure out area that's touching either the floor or a table, whatever you have it on. And we need to look at the weight. In this instance right now, my height does absolutely nothing for me. We will use it a little while later, but right now what's important is my surface area, so my area that touches the table. So we've got 2 inches and 3 inches. In the defined area, we do length times width. Area is equal to, doesn't matter which one you want to do, but let's say it's 3 times 2, so 3 inches times 2 inches. Okay, my camera just died there, so I was working to get everything back up and going. So what I was saying, so we've got 6 inches, so inches squared, okay, from that, so 3 inches times 2 inches is 6 inches squared, and we've got 60 pounds, so we can bring this over here, and we've got a force, and the video won't be too much longer. We've got a force of 60 pounds, and it's 6 inches squared, and when we divide that out, and we want to look at what our pressure is, we find that we have a pressure of 10 pounds per square inch, or 10 PSI, okay? Or you could do pounds per square inch, like that. So we know that we have 10 PSI. Now, what I want you to look at with this is for pressure, is that right now all of our pressure is focused on one area. And if we end up changing this, so I'm going to erase all this, and I'm going to lay that same column sideways. A little curvy there. So that was 60 pounds. It's 15 inches, 3 inches by 2 inches. So now I want to calculate what the pressure is that's being exerted on the ground now. So what information is important? I still have my force of 60 pounds, but now I'm not using this 2 inches here. I'm only going to be using my 3 inches and my 15 inches. So I'm going to take formula. I'm going to take my 60 pounds for force. I've got 60 pounds. Divide that by 15, or 3 times, so 3 inches times 15 inches, and I get a value of 60 pounds, hopefully you can see that, divided by 45 inches squared. And if I go to put that into my calculator, we should get a value of, I believe it would be, pressure is equal to 1.33 psi. So I went from 10 psi down to 1.33 psi. So let me just calculate that so I'm not just saying it is what it is, although I think it is. We got 60 divided by 45 and we get, yeah, 1.33 repeating psi. So that's just like what they say when you're on thin ice, to lay down, it ends up spreading out the amount of force or that you're applying to the ice. So rather than standing, in this case, this block, which was doing 10 pounds per square inch, now we're only looking at 1.33 pounds per square inch as we end up spreading everything out. So that's something extremely important to think about. I'm going to leave one more with you, and then I want you to attempt to pound out the math on it. So it's going to be, let's do 30 inches by 40 inches, and it's 20 inches high, and it's going to be 150 pounds, and then when it goes the other way, it's going to be this should have been all out of the way, but what's going to be on the ground is the 30 inches by 20 inches is going to be on the ground. So it'll be the 40 inches that's going up and down. Okay, so calculate that out. There it is there. So this end is on the ground, the 20 by 30, where in this case it was this that was on the ground in this scenario. Okay, so before our lab class, if you could work that math out, and then we'll take that up in class, that'd be very much appreciated. Okay, have a good day, and I will see you next week. And sorry for this video. I didn't realize the camera had died, so I'm having to add this in after the fact. So I will see you guys next class. Okay, bye.